Welcome to The Explainer. Today, we're diving right into a fascinating look at the everyday chemistry happening right under our noses. Or, well, actually, right inside our kitchens. You might not even realize it, but every single time you brew a steaming cup of coffee, or violently shake up a pre-workout drink, or even simmer a really complex savory soup on the stove, you're actually conducting a highly precise chemistry experiment. We're going to explore the invisible science that governs these everyday materials. Specifically, we'll look at how different substances physically interact and bind together to form what chemists call solutions. And oh man, we are going to uncover the incredibly powerful, sometimes volatile role that temperature plays in manipulating that whole shebang. Now, don't worry, this isn't abstract textbook theory. It's highly practical, foundational science. It's literally a molecular choreography that you are orchestrating every single day without even realizing it.
Okay, let's dive into this by confronting a concept that directly challenges a super common, deeply ingrained misconception. Think about the last time you stirred a spoonful of raw sugar or maybe coarse salt into a glass of water. You watch it swirl around for a few seconds, right? And then, poof, it seemingly vanishes before your very eyes. But what's actually happening in that glass? Does the solid material just disappear into nothingness? Does it melt? You know, the way an ice cube turns into a puddle on a scorching summer day? Or is it doing something else entirely? We casually toss around the word melt in the kitchen all the time, but scientifically speaking, melting is a thermal reaction. It strictly requires the application of heat to force a solid phase into a liquid phase. So what we're actually witnessing in that room temperature glass of water is a completely different, entirely invisible mechanical process.
Here's our agenda for today. We're covering 1. The magic of mixtures. 2. Solute versus solvent. 3. Water, the common solvent. 4. The limits of solubility. And 5. Turning up the heat. Let's get started with Section 1, the magic of mixtures. So, to truly grasp what's happening here, I want you to mentally picture your kitchen counter. Just imagine it. On it sits a clear glass of plain, pure water. Right next to it, imagine a second glass of water, but into this one, you've just stirred a packet of finely milled, intensely colored powdered juice. Both are liquids, right? Both are sitting perfectly still on the counter. But structurally, they are fundamentally different. What you've engineered in that second glass is a true solution. A solution is a uniform mixture formed when a solute dissolves in a solvent. The absolute critical word there, the one you really got to remember, is uniform. To a chemist, uniformity is what separates a true, elegant solution from just a messy, chaotic combo of random ingredients floating around together. Uniform means that the dark red juice powder hasn't vanished from reality, nor is it just lazily sunk to the bottom as sludge. It's mixed so thoroughly, so completely, and honestly so aggressively into the water that the entire volume of liquid looks, tastes, and behaves the exact same from the very top drop to the very bottom. The physical material is completely intact. It's just perfectly molecularly distributed. Moving right along to Section 2, solute versus solvent. So, how exactly do we achieve this perfect, uniform equilibrium? Well, every single solution in the world, from a massive ocean to a tiny teardrop, is made up of a specific cast of interacting characters. Identifying them is the absolute foundational key to unlocking how they work. Our first character in this dynamic duo is the solute. By definition, the solute is the substance that dissolves in another substance. Think of it as the material that's just waiting to be acted upon. If you're preparing a glass of intensely sweet sugar water, that crystalline sugar is your solute. If you're mixing up a sterile saline wens for a contact lens, the dense granular salt is the solute. It's the vulnerable solid, right? Its chemical bonds are just sitting there, ready and waiting to be broken down, invaded, and scattered. Now, the second indispensable character here is the solvent. The solvent is the substance that physically dissolves the solute. This is the active, aggressive agent in our chemical drama. It is the surrounding environment where all the violent mixing and tearing apart actually happens. Basically, the solvent is the material doing all of the heavy lifting. In almost all of our standard culinary examples, like that glass of sweet sugar water or the briny salt water we just talked about, the surrounding liquid is acting as our solvent. And here's the crazy part. It doesn't just passively sit there while the solid breaks down. Oh no, it actively attacks the solid structure, pulling apart the solute molecule by molecule, and then carries those tiny pieces, spreading them completely uniformly throughout its own volume. And this brilliantly illustrates the easiest way to tell them apart in your own kitchen. You don't need to look through a microscope. You just need to analyze sheer volume and mass. The solute is almost universally the material present in a vastly smaller amount. Picture a single concentrated teaspoon of dense white sugar. The solvent, conversely, is the material present in a much, much greater amount, like a tall, heavy 16-ounce glass of water. It's really a game of ratios. A tiny, highly concentrated bit of solute is always surrendered to and frankly overwhelmed by a massive, enveloping volume of solvent.
All right. Section 3. Water, the common solvent. Now, these definitions aren't just locked away in some sterile laboratory somewhere. They're the underlying code of literally everything we consume. Let's go on a quick household hunt and map out a simple matrix of everyday culinary elements to see this vocabulary in real action. When we analyze standard mixtures, a clear pattern emerges. In basic salt water, the granular salt represents the smaller mass being overwhelmed, making it the solute, while the liquid water acts as the solvent. In a rich protein shake or powdered milk drink, that dense, dry milk powder is the solute waiting to be broken down by the water solvent. Even brewing your morning coffee, that's just the act of creating a dark, complex solution where roasted coffee compounds act as the solute, completely surrendering to the surrounding water.
The undeniable through line in all of these daily rituals is the sheer dominance of one specific liquid. In the vast majority of our common, everyday solutions, the solvent is water. Water is incredibly, almost ruthlessly effective at pulling apart solutes to force those uniform mixtures. Because of its unique molecular shape and its slight electrical charge, water acts kind of like millions of tiny chemical magnets, locking onto other molecules and ripping them away from their solid structures. From extracting the bitter caffeine compounds from a roasted bean to dissolving the rich collagen proteins in a bone broth, water is the universal workhorse of our food systems, quietly and efficiently dismantling our daily solutes.
Let's shift gears to Section 4, the limits of solubility. Imagine we're lab partners for a second. Let's observe a fundamental mechanical process in real time, moving from a resting state to dynamic equilibrium. First, step 1. In a completely undisturbed state, before any agitation whatsoever, you just see a dense pile of solid white salt sitting rigidly at the bottom of a glass of clear water. It's separate. It's intact. Then comes step 2, the mechanical introduction. During rigorous stirring, the environment gets completely chaotic. The water turns deeply cloudy as that organized pile of salt starts to structurally fail, break apart, and wildly swirl around the glass. Finally, step 3. After the mechanical energy stops and the mixture settles, the liquid is completely, perfectly clear again. The chaotic, cloudy phase is ended, and the solid has been seamlessly integrated into the liquid matrix. But witnessing this seamless integration inevitably leads to a thrilling, boundary-pushing question. Can water dissolve an unlimited amount of salt? I mean, what happens if we intentionally try to break this chemical system by pushing it to its absolute physical extreme? Picture a tiny espresso cup, barely filled with a quarter cup of water. Now, instead of a delicate pinch of seasoning, imagine dumping in 3 massive, heaping tablespoons of coarse salt and stirring as furiously as humanly possible. Will the water still be able to tear all of that solid apart and return to a clear, elegant solution?
So the crucial point is this. No, it cannot. The system completely fails. If there is drastically too much solute and not nearly enough solvent, the solute will simply refuse to fully dissolve. It literally does not matter how aggressively you stir or how much kinetic energy your spoon brings to that tiny espresso cup, the excess salt will defiantly remain a solid, gritty pile at the bottom. And the reason is entirely mechanical. The solvent has reached its maximum literal capacity. You can kind of think of the water molecules as having only a finite number of microscopic hands available to grab onto the salt ions. Once every single water molecule is holding onto a piece of salt, there are no more hands left to do the work. The solvent is entirely occupied, and the remaining solid is left completely untouched.
This hard, natural limit brings us to one of the most absolutely crucial metrics in all of chemistry: solubility. Solubility is the strict, quantifiable ability of a specific solute to dissolve in a specific solvent at a specific temperature. It isn't just a vague concept, It's a rigid mathematical threshold. When food scientists are engineering the perfect sports drink, or even when you're just trying to maximize the flavor in a pan sauce, you are constantly navigating solubility. You're testing exactly how much flavor, sugar, or sodium a specific volume of liquid can physically hold before it structurally gives up and stops dissolving. Every single solute-solvent pair in the universe has a unique, unbreakable solubility limit. Which brings us to our final act, Section 5, turning up the heat. Now, what if I told you there's actually a brilliant way to hack this mathematical system and bend the strict rules of solubility? We can introduce a catalyst.
let's do another quick kitchen stress test comparing cold water against hot water. If you drop a dense tablespoon of fat-heavy milk powder into ice-cold water, you're met with immediate resistance. It stubbornly clumps together, floating on top as a dry, powdery mess, dissolving agonizingly slowly no matter how hard you whisk. But if you introduce that exact same milk powder to steaming hot water, the integration is almost instantaneous. The powder gives way effortlessly, dissolving incredibly fast and seamlessly right into the liquid. Now, what's really interesting about this slide is the invisible mechanism making that happen. As the quote says, the particles move faster. The secret behind this dramatic transformation lies entirely in the speed of those particles. Heat, in the realm of chemistry and physics, is quite literally just kinetic energy. When you apply a flame or a heating element to a pot of water, you are injecting massive amounts of raw energy into those water molecules, causing them to vibrate and zip around at incredibly high velocities. The hot solvent effectively becomes a microscopic, high-speed demolition derby. These highly energized, fast-moving water molecules crash into the solid solute structures with exponentially more force and frequency. They act like tiny jackhammers, relentlessly and violently ripping the solid apart and dissolving it far more efficiently than the sluggish, lethargic molecules of cold water ever could. Heat is, for sure, the ultimate solubility hack. In this invisible, microscopic violence is the driving engine behind our most essential daily routines. When you're extracting coffee, you intuitively use boiling water because you need that high-speed kinetic energy to strip the complex oils and caffeine out of the dense bean. When you're developing a rich, deeply flavored soup base or reducing a soy sauce marinade, you're utilizing heat to expand the water's solubility limit, forcing it to hold way more savory compounds than it ever could at room temperature. But this also has serious safety stakes too. In emergency medicine, when mixing life-saving oral rehydration solutions for severe dehydration, understanding the exact safe and proper ratios of solute to solvent ensures the mixture absorbs into the bloodstream correctly, rather than causing further cellular damage. It's exactly why reading product labels and understanding these foundational chemical limits is absolutely vital. So the next time you're standing at your counter pouring a steaming hot cup of dark roast, or vigorously shaking an ice-cold electrolyte-heavy sports drink, take a real moment to look at the liquid. Ask yourself, how are temperature and physical quantity actively controlling the chemistry in this cup right now? Because you're not just making a quick beverage, you are an active chemist. You're masterfully balancing dense solutes, fluid solvents, and raw kinetic heat to engineer the perfect, uniform solution. Keep observing the invisible mechanics around you, keep pushing the boundaries, and enjoy the brilliant science in your very next glass.